Okay, thank you very much. And yes, I'd just like to again thank all the organisers for the conference. It's been really great conference, very enjoyable. So thanks very much. So what I'd like to do today is talk about one kind of approach to perhaps finding rigorous and effective algorithms for computing hyperbolic structures. So for instance, so SNAPPy seems to work very well in practice, but one of the problems there is coming up with good ideal triangulations. In particular, we'd like to come up with, say, a topological triangulation which can be realised geometrically by positively oriented ideal hyperbolic tetrahedra. And I guess this still seems a very difficult problem in general, but I want to talk about one approach to this today which uses the idea of angle structures. Okay, so for today we're going to start with, say, a topological manifold which is compact orientable. The boundary consists of incompressible tori. So for example, a good example is you take a knot in a three-sphere and you remove a tube around the knot to get a manifold with torus boundary. Okay. Now we know from Thurston's hyperbolization theorem, say for Harkin manifolds, so if the manifold's irreducible, atoroidal and acylindrical, then the interior has a complete hyperbolic structure of finite volume. I guess maybe I should just remind you, so irreducible means that every two-sphere bounds a ball. Atoroidal means there's no incompressible tori in the manifold. So any torus there's no torus whose fundamental group injects into the manifold. Acylindrical means there's no kind of essential annuli or cylinders in the manifold. And these are nice to topological conditions that guarantee existence of a hyperbolic structure. And I guess we know from osteoprigidity this hyperbolic structure is unique. So then you get all these kinds of nice geometric and arithmetic invariants for your manifold. But yeah, so the basic question I'm talking about today is how to compute such a hyperbolic structure. Now, I guess we've seen a very powerful technique for doing this, and this goes back to Thurston and Jeff Weeks in the program SNAPPy, which is using ideal triangulations. So here's kind of a quick replay of what we've been doing already. First, we decompose the manifold topologically into ideal tetrahedra. So these are just tetrahedra with the vertices removed. And this is just a topological kind of description of the manifold. Then we have to find shapes for the ideal tetrahedra. We want to find tetrahedra in hyperbolic space which fit together correctly to give a hyperbolic structure on the interior of this manifold M. So this is exactly what we did for the figure 8 knot example, for instance. And in practice, works extremely well. And we have this beautiful program of Jeff Weeks called SNAPPy, which implements this method very, very nicely. And this works very well you can work with extremely complicated examples. You could start with knots with maybe 50 or 100 crossings, and this works extremely well. But one of the key things is to kind of find a good triangulation to start with. Okay. So for this process to work, you need to find, first of all, okay, so there's a few basic questions here that I want to think about. First question, can you find an ideal triangulation by positively oriented ideal hyperbolic tetrahedra? So this is what you want if SNAPPy is going to work successfully. Now this question, as far as I know, it's still open in general if you start with a hyperbolic 3 manifold. The answer is yes if you allow some flat ideal tetrahedra. So If we take our complex parameters, if you allow the complex parameter to become real, that amounts to the sort of three-dimensional tetrahedra flattening out to a two-dimensional thing. If you allow that, then you can get such things. For instance, there's this nice canonical ideal cell decomposition, say, of Epstein and Penner. That gives you a decomposition into ideal hyperbolic tetrahedra. And you can always subdivide it into tetrahedra. But there's a question about consistency. When you subdivide, you might have to insert some flat tetrahedra. Okay. But this is almost, because in practice this is good enough to do the computations. It's also known that the answer to this question is yes, if you go to a finite sheeted cover of your manifold. So some work of Feng Lo, Sol Schleimer and Stefan Tillman, which shows you can get a positively oriented triangulation if you go to a finite sheeted cover. On the other hand, if you're just given your manifold topologically, you'd just start with some kind of random triangulation of your manifold. What you'd really like to do is some kind of algorithmic way to come up with a good triangulation which corresponds to sort of a geometric triangulation with positively oriented tetrahedra. So this is a really important question from the computational point of view, and it's very much still an open question. So, okay. Now, there's another kind of basic question. If I give you some topological triangulation of this hyperbolic manifold, say, you'd like to know, does it really come from a geometric decomposition into ideal tetrahedra? So you might think of it, can it be realized geometrically by positively oriented ideal tetrahedra? So you can ask this if you start off with any triangulation of some manifold. Yeah, is it really a geometric triangulation? And of course, in general, the answer is going to be no. It might correspond to something with some negatively oriented tetrahedra. And then it's not, yeah. So if you have a combination of, say, solutions to Thurston's gluing equations with some positively oriented and some negatively oriented solutions, it's not clear that you've got a hyperbolic structure or not. So you can't really tell without doing, some other kind of analysis. But anyway, if you have a sort of geometric realization, that does put some topological conditions on the triangulation. For instance, the edges of the triangulation are isotopic to geodesics in the manifold. And that implies, for instance, you can't have little knots tied in the edges. So there's some sort of restrictions on the kind of triangulation for this to happen. But again, it's very much open. Can you find sort of nice topological conditions which can be realized geometrically? Okay. So what I'd like to do today is talk about one way to sort of approaching this kind of question. And I guess this uses the idea of angle structures. And there's going to be some kind of volume maximization procedure which allows us to try and find the hyperbolic structure from an angled structure. Okay. So we're actually going to look at some kind of space of angled structures which are some sort of singular hyperbolic structures. And the basic ideas here go back to Igor Rivin. So here's a nice paper in the Annals of Mathematics about 1994. Originally he was studying convex ideal polyhedra in hyperbolic space where you prescribe the dihedral angles. So if you give the combinatorics and some numbers attached to the edges, question is, can you realize that by a hyperbolic polyhedra in hyperbolic space? And it turns out there's actually very nice answers to that question. And I guess Riven's approach here was some kind of volume maximization procedure. So we're going to try and extend this now to kind of manifolds. Okay. So first of all, so we've seen how to parameterize shapes of ideal tetrahedra in H3. One way is to use these complex edge parameters that we've been talking about the last few days. Another way is just to keep track of the three dihedral angles along the edges. Now remember, we had sort of three different edge parameters, and each of those complex parameters corresponds to one dihedral angle. So in fact, if you take the argument of the complex number, that gives you the dihedral angle. So if we just stick to angles, so we have three numbers attached to the tetrahedra, say alpha, beta and gamma. They correspond to the angles in a small sort of Euclidean triangle, which is a cross-section by a horosphere near the vertex. So you can see, if you look at this first vertex, the angles alpha, beta, gamma have to add up to pi. This is a
Yep. If one of the angles is negative, is still the sum of pi or...
Well, we actually want geometric tetrahedra. So today, they're always going to be real triangles, and the angles are going to be positive. Yeah.
How about your problem? Is your problem contain negatively oriented?
If you go back to Snappy, that will work with negatively oriented tetrahedra, but I'm not going to be looking at that today.
So then, if there to have a solution, you have to have a redundant equation, one redundant equation, and that comes from the cusp. If it is a not complement.
Yep. Okay.
And I realized that if I have one redundant one, then the edge sum has to be all 2 pi, right?
Mm-hmm. So, okay. Yeah. Yeah, I mean, we'll see that today as well, again. Okay, but for today, I really want geometric tetrahedra, so all the angles should be positive. So they're just ordinary Euclidean triangles. The angles are positive, and they should add up to pi. Okay, so maybe we can talk later for more. Yeah, okay. But, okay. So if you look at, so the same is going to be true at each of the vertices. The angles have to add up to pi because they're all Euclidean triangles. And in fact, you can easily see that means that opposite edges have the same angle. So if we have alpha here, there's also alpha here. If we have alpha on this front edge, there's beta on the back and beta on the front. Okay, and gamma here and here. So that's kind of the picture of the angles for any ideal tetrahedron. So this gives you a kind of nice parameterization of the shapes by looking at angles, say alpha, beta and gamma, where all the angles are between 0 and pi, because I really want a geometric tetrahedron. And we have this, so these are inequalities on the angles together with the condition alpha plus beta plus gamma is equal to pi. So if you think about this, so what we've got, if we think about this sort of space of angles at alpha, beta, and gamma, this is going to give us some kind of a triangle. So it's an open triangle like this. Okay, so it's actually open. Points on the boundary are excluded. So that's going to be my delta. So that's describing the shapes for these ideal tetrahedra using angles. Okay, so that's kind of the starting point for today. So we're using angles instead of these complex parameters. Okay. So now if we've got one of these manifolds, so for instance something like a knot complement, and we have a topologically ideal triangulation, say T. Okay. Let's suppose we start off with n tetrahedra altogether. then it's a nice little exercise to show that the number of edges is also equal to n. So that just uses the fact that the Euler characteristic is equal to 0. Okay, so we have n tetrahedra, and we also have n edges in the triangulation altogether. Now let's suppose we just pick kind of arbitrary shapes for all of these n tetrahedra. And that will give us a point in the product of n copies of this triangle delta with itself. Okay, so for the first tetrahedron you get some point in the first triangle. So you just write down the list of all these dihedral angles, and that lives in delta to the n, which is sitting inside r to the 3n. Okay. Now if you take any kind of choice of shapes for the ideal tetrahedra, you can glue the faces together, as we've seen, and you end up with a hyperbolic structure on M minus the complement of the edges. Okay, but there might be some sort of singularities along the edges. Okay. And okay, so for a complete hyperbolic structure, we need some conditions. First of all, the sum of the dihedral angles is 2 pi around each edge. Okay, so that's kind of the obvious condition. Because we have infinitely long edges, we also have this kind of no translation condition. There's no kind of translational singularities along each edge. So geometrically that means something that, like, there's no kind of shearing along the edge. And so this happens because the edges are infinitely long. You have to worry about this. And finally, these two conditions will guarantee some kind of incomplete hyperbolic structure, but we also need completeness conditions at each cusp. Okay, so these are all conditions we've seen before. First one's kind of an obvious condition. The second condition, okay, one way to think about it, if we look at horospherical triangles orthogonal to the edge, they have to fit together nicely around each edge. So you might have some sort of picture like this. The angles here add up to 2 pi, and these sort of triangle cross-sections all fit together to give you a kind of nice closed disk. Sort of thing that could go wrong is you might start off with one triangle, you go to the next triangle in the next tetrahedra, you keep going around the edge, and you might come back, even if the angle's 2 pi, you might get a different length to what you started with. So you might go around and come back with a different length. So this is kind of the situation we want to avoid. And this would give you some kind of shearing along the edge, in fact. And there's a similar sort of condition picture for condition 3. You can start, you get a sort of nice triangulation of the torus by the corners of tetrahedra. You map it, you take the developing map, you start mapping it into a horosphere, and you want to get a nice Euclidean structure on this torus. Okay. Yep.
So you're given a topological triangulation.
Yes.
If we allow the negatively oriented tetrahedron.
I'm not allowing them today. Okay, so we're not going to allow them. Okay.
I'll talk about it later.
Yeah. So maybe so today we want to avoid them because they're bad. Okay. So maybe let's talk about it later. Yeah. Thanks. Okay. All right. So now, okay. So we've got these equations. Let's just go back. Now it turns out another way to write these conditions, these first two conditions, is in terms of the complex parameters. We get some kind of product of complex parameters equal to 1 around an edge. But that's some sort of nonlinear system of equations. So they're actually complicated equations. And to try and understand this, what I'm going to do is break the problem up into two pieces. So first we're going to have a kind of simple linear set of equations, and then we'll have a second part which is a nonlinear part. So that's the basic idea behind the angle structures. Okay. So the first step, we're just going to look at these angle sum equations. So these are nice linear equations. saying that the sum of the angles as you go around each edge is equal to 2 pi. So it's a system of linear equations. The angles have to lie in, for each tetrahedron, they lie in this triangle. So you'll have these kind of extra conditions. The sum of angles is pi for each tetrahedron, and all the angles are greater than 0. So you have some linear equations, and you also have some inequalities. So this actually is some kind of linear programming problem. You've got linear equations and inequalities. And if you solve this, you get some kind of convex polytope. So it's some sort of convex set. And we're going to call this the set of angle structures, A of t. So solutions to this are called angle structures on our triangulation. And this is sitting inside, okay, the space of all possible angles was delta to the n, and that's contained in R3n. If you take the closure of this, you get a nice compact convex polytope, because it's contained in this compact set, a closure of delta to the power n. That's just a product of closed triangles. Okay, so these angle structures, they go back to work of Casson and Riven. I think they were the first people to really look at these. And they've actually proved to be quite useful for a number of different problems. So they've been used nicely by people like Lakenby, Gerito Futa, and a number of others to solve interesting sort of topological problems. Okay. Okay, what do these angle structures geometrically, they give you some sort of singular hyperbolic structures on your manifold. You have hyperbolic structures with kind of shearing happening along the edges. So this is kind of a schematic picture. So if you're living inside this manifold and you see what happens across the edge, well, if there's no shearing, okay, so we see someone across the other side of the edge. But if you have these kind of shearing singularities, so the edge is in the middle, and you get some kind of shifting. So one side of the face gets shifted. So that's kind of the bad case. But that's what angle structures are geometrically. Hyperbolic structures with kind of shearing along the edges. Okay. Okay. Now at this stage, I thought let's just do a concrete example to see, okay, what do these equations for angle structures look like? So I'll go back to a favourite example, figure 8 knot complements. So as we had the other day, you can form the complement by gluing together two ideal tetrahedra. So basically here the edges get glued together according to this pattern. And I guess from the kind of gluing pattern on the edges, you can actually work out how the faces fit together. So this is the picture we had previously. Now, if we go back to our complex parameters, so z prime, z double prime, w, w prime, w, w prime. Okay, we saw last time the edge equations say product of parameters around each edge is equal to 1. So that gives us two equations like this. I guess the first equation came from the blue edge, second equation came from the red edge. Okay. Another way to write these, we could take logarithms of both sides, and the conditions we want in logarithmic form look like this. So you'll get something like twice log z plus log z primed plus log w plus twice log w prime. That's supposed to be 2 pi I. 2 pi I is saying that the sum of all the angles is actually equal to 2 pi. So that's what you get from the first equation, and you get something similar from the second equation. Now these equations have got two parts. So there's a real part. The real part has to be equal to 0. The imaginary part has to be equal to 2 pi I. And if we take the imaginary part, we're getting exactly these angle structure equations. So we want to take the imaginary part of these equations. So let's see. So what do we get? Well, in the first equation, the imaginary part of log is the argument of z, and that's going to be kind of the first dihedral angle along this edge. So let's see. So if I write, say, alpha 1, beta 1, gamma 1 for the angles in the first tetrahedra, and alpha 2, beta 2, gamma 2 for the angles in the second tetrahedra, then the angle structure equations are very simple. First we get linear equations. This is saying the angles around the first edge add up to 2 pi. Second equation says the angles around the second edge add up to 2 pi. We also have the conditions that in each tetrahedron the angles add up to pi. So that gives us 2 more equations. And for a positively oriented tetrahedron, so for a geometric solution, all of the alphas and alphas, betas and gammas should be positive. So this is exactly what we have to solve to find angle structures on the figure 8 knot complement. And you can see it's exactly a kind of linear programming problem. We've got linear equations and some linear inequalities. Okay, so that's kind of typical of what's going to come up in general. And these things are very easy to solve. There's lots of nice efficient algorithms for doing linear programming. So these can be solved very easily. And what you expect is some kind of convex polytope of solutions to these. Okay. Okay, so finding angle structures is quite easy for a given triangulation. Now, if you find such an angle structure on a topological manifold, that already gives you some sort of nice topological information. So for instance, okay, first of all, if you have, say, a compact manifold with boundary, the existence of an angle structure means the boundary is made up of tori. Or you could have Klein bottles if we're working in non-orientable case. You also get the topological conditions that M's irreducible and A toroidal. So if you can find one of these angle structures, you already get a lot of topological information about your manifold. Okay. So the basic problem is kind of a linear programming problem. And there's kind of nice duality results in linear program which allow you to rewrite these conditions. And there's also another way of writing the conditions in terms of normal surfaces. So I won't say much about that today, but yeah, there's a nice paper of Feng Lo and Stefan Tillman which describes how to write these conditions in terms of normal surfaces in your triangulation. Okay, so these angle structures, they're fairly easy to understand, and they can be computed, for instance, using Ben Burton's program Regina for studying normal surfaces. Okay, so this is the first part of our procedure to find hyperbolic structures. First, we do this kind of linear programming problem and find solutions for this. Okay. Now, the next part is, okay, how do we deal with the remaining nonlinear equations? And, okay. So the nonlinear equations basically come from saying that there's no translations along edges and the completeness conditions. So that was these conditions 2 and 3. And the way we're going to do this is by a kind of volume maximization procedure. Okay. So to start off, what we're going to do is define a volume function. So if we start with an angle structure, we have some kind of shape for each of the ideal tetrahedrons. So an angle structure gives you a shape for each of the ideal tetrahedron in our triangulation. Okay. And the idea is to add up the hyperbolic volumes of all these ideal tetrahedra. Another way of saying it, we have this kind of singular hyperbolic structure with shearing, and we just take the volume for this singular hyperbolic structure. So that's a nice function on the space of angled structures. Okay. So I want to say a bit about how we can compute this volume. Okay. So the starting point is just the volume for an ideal tetrahedron. Now, I guess, so Walter described one nice way to write this in terms of the dilogarithm function of the complex parameter. I'm going to describe another way to do this in terms of the dihedral angles for your tetrahedron. And, okay, so if we have angles alpha, beta, gamma, then you can write the volume as the sum of so-called Lobachevsky functions of those three angles. So here, okay, the Lobachevsky function, this kind of L of alpha, it's defined by this integral. It's minus the integral from 0 to alpha of log of 2 sine t dt. Now you can check that this integral gives you a nice continuous function. The way it's defined here, it's going to be 0 when alpha is equal to 0. And you can actually extend it to a nice continuous function on all possible angles alpha. So I guess, I'm not going to prove this today, but a nice reference for this is the article of Milner on, I think it's called Hyperbolic Geometry, the first 150 years in the Bulletin of the AMS. So this is a nice reference for this kind of calculation of volumes via the Lobachevsky functions. Okay, so this gives us a nice explicit way to calculate the volume in terms of the angles. And I think, yeah, so here I've got a picture. So here's a graph of the Lobachevsky function, say between minus pi and pi. You can see, okay, so first of all, we know when the angle is 0, the function's 0. It's actually an odd function, so this part of the picture on the right, if you rotate 180 degrees, you get this part on the left. So it's an odd function of alpha. It has a maximum. Well, so this maximum you can easily figure out by looking at the integral formula. Oh, let's go back here. So when's the derivative of this function equal to 0? Well, it means that log of 2 sine t is equal to 0. That means that 2 sine t is equal to 1. So sine t is equal to a half. And then that gives you, say, t is equal to pi over 6. So, in fact, so this maximum, I guess, occurs when the angle is pi over 6. Okay. Okay, so that's what this function looks like. It's actually a nice, it's a nice differentiable function, I guess, except at the origin, I think. Now at this stage, one thing you can prove easily, you could find, okay, what's the maximum possible volume for a tetrahedron in hyperbolic space? So let's allow finite vertices or possibly vertices on the sphere at infinity. So those will have finite volume. Question is, okay, what's the maximum volume you get? Well, if you think about this a bit, if you take a compact tetrahedron, you can always increase the volume by moving the vertices out to infinity. So certainly the maximum volume has to occur for some ideal tetrahedron. And I guess you might guess that maybe the most symmetric one should have the maximum volume. And in fact, so that's true. So if you take the regular ideal tetrahedron, so that's one with all dihedral angles 60 degrees, that's the unique tetrahedron with maximum volume. And okay, so I'll leave this as a little exercise using the formula for volume in terms of Lobachevsky function. But what you need to do is maximize this sum, this Lobachevsky function of alpha plus beta plus gamma, but it's subject to the constraint that the angles of our tetrahedron have to add up to pi. Okay, so maybe, let's see, so who can solve this problem? How should we solve this problem? So who can tell me? We've got to maximize a function subject to this constraint. So what's a standard way of doing this? Who can tell me? What about, okay, what about one of the students? Yeah. So the standard kind of way to do this is using Lagrange multipliers. And I'll leave you to try this as an exercise. But this is going to be kind of a simple case of what we're going to do to understand volume maximization when we have a triangulation of a three-manifold. So again, it's going to be a kind of a Lagrange multiplier argument, basically. Okay. So if you're getting bored, you should try doing this little exercise. Okay. So now, if we go back to our angle structures, okay, we get this volume function by adding up the volumes of all the ideal tetrahedra. And this has got some nice properties. So first of all, it's actually a nice continuous function, and it extends continuously to the closure of this angle structure space. So that's allowing some of the angles to go to 0 or pi. So we've got a continuous function on a compact set. So we know this function must have a maximum somewhere on this closure of the angle structure space. Now, I guess if you look at the previous picture of this function, so if you look here, for instance, it's actually a nice, it's a concave down function. It's always curving down like this. And I guess if you look with a bit more work, you can show the volume function. Again, it's strictly concave downwards on the whole of the angle structure space. So that's not too hard to check. And I guess Riven was probably the first one to notice this and use this fact. So if we've got this volume function, okay, so so roughly we've got, looks something like this perhaps. So that tells you, this concavity tells you there has to be a unique maximum in the interior, if there is a maximum in the interior, which is this angle structure space. Okay, so you get kind of uniqueness from this concave property for the volume function. And so what is this maximum? Well, here's the basic theorem I want to talk about today. If the volume has its maximum at one of the interior points, so that's at one of these angle structures, then that corresponds to the complete hyperbolic structure on M. So maximizing volume picks out the complete hyperbolic structure on this manifold. Okay. And I guess this uniqueness from the concavity also shows that this hyperbolic structure is unique. So this actually, okay. So let's see. So now if we're given an ideal triangulation, the problem of finding this hyperbolic structure is broken down into two sort of parts. So if we can find a triangulation, so the set of angle structures is non-empty, so that will give us some region to work with. And then we try and do this volume maximization. So if the volume has no maximum on the boundary of this space of angle structures, then, okay, the volume occurs at an interior point, and this theorem shows it must give you the complete hyperbolic structure. And this is going to, it comes from a positively oriented ideal triangulation. So at the interior points, all the tetrahedra, they're actually positively oriented hyperbolic tetrahedra, and you get a nice geometric triangulation for the manifold. So this procedure, when it works, so first of all it computes a hyperbolic structure. It also shows that the triangulation you started with is actually geometric. It can be realised by positively oriented tetrahedra. Okay. Now at this stage you can start kind of trying to use this to various sort of families of examples. And I just want to mention two cases where this has been carried out very nicely by the work of Gerito and Futa. So one case is the case of once punctured torus bundles. So these are manifolds that fibre over the circle with a once punctured torus as the fibre. And so Gerito is, in this case, there's a nice kind of standard triangulation you get by looking at the monodromy, the gluing map for this bundle over the circle. So there's a nice kind of combinatorial triangulation that comes from the gluing map for the bundle. And okay, so what Gerito showed was to use some kind of procedure like this, looking at these angle structures, ruling out the possibility of a maximum on the boundary, and that guarantees you actually that this triangulation is geometric. So the kind of monodromy triangulation is geometric, and that gives you a hyperbolic structure on this bundle. Okay, so this is in the case where the gluing map, it's actually a pseudo-anisoft gluing map. There's a few exceptional cases which are not hyperbolic. Let's see what else. And in fact, by a little bit more work here, Gerito can actually show that these sort of standard triangulations are actually the canonical triangulations for the punctured torus bundles. So you can also identify sometimes the canonical triangulations. I guess there's also a version of this for two-bridge knot complements, which was worked out, I guess, by Gerito and Futa. In this case, again, these have nice sort of standard topological triangulations, and this angle structure procedure shows that the sort of standard triangulations are actually geometric. Okay. And again, I guess they're actually canonical triangulations. Okay, so there's a few examples, but this seems a kind of very promising approach that you could hope to apply to other sort of interesting families of three manifolds. Okay. Now, I guess you might hope that this kind of procedure will work in general, and I guess there's a question, or maybe a conjecture, which probably goes back to Igor Riven, that if you just start with a manifold with these sort of topological properties, it's irreducible, atoroidal, and acylindrical. Okay, so actually we know in this case the manifold should be hyperbolic by Thurston's theorem. But the question is, the conjecture is that you can find a topological triangulation so that the space of angle structures is non-empty. So this is kind of a weaker version of the question that I put up at the very beginning. If you're given a hyperbolic manifold, can you find a geometric triangulation? Well, that seems very hard, and this is a kind of slightly easier question. So you could ask, can you find a triangulation where there are angle structures? And that should be a bit easier to understand. So, okay. Okay, so what I'd like to do now is go back to this theorem. I want to show that if the volume has a maximum at a point in this angle structure space, then it gives the complete hyperbolic structure on M. So I'd just like to, the rest of the time today, I want to look at an outline of the proof of this. Okay, so first a bit of notation. So I'll write A for the set of angle structures on our triangulation T. I'll write N for the number of tetrahedra, and that's also the number of edges. Now, okay, first we want to think about these angle sum conditions. So each of the angle sum conditions gives you a linear equation. If you put these together, you get n linear equations altogether, and you can think of this as described by a linear function from delta to the n. That was all kind of, so all possible kind of angles for tetrahedra. Given a set of angles, you write down the angle sums around the n edges, and that gives you a function into Rn. Okay. So if we go back to our figure 8 knot example, we had 6 angle parameters, so we'd be working in r to the 6. We had 2 angle sum equations, that gives you a linear function mapping into R2. And the angle structures we want, it's just the pre-image of this point where all the coordinates are equal to 2 pi. Okay, so here's one way to think about the angle structure space. It's the inverse image of this point under the linear function g. Okay. Now, so to analyse this, I want to think about basically the derivative of this function on delta to the n. So first of all, if we take the tangent space to this delta to the n, it's basically a product of planes. So if you take one of these deltas, it's contained in a nice two-dimensional plane. The tangent space is the corresponding subspace through the origin. So if you take the product of these, you get a product of n of these two-dimensional subspaces, and that's a 2n-dimensional vector subspace of Rn. So I'll call that W. So if you think of deforming the angle structures, you're moving inside this 2n-dimensional vector space W. Okay. Now, if we take the derivative of this function, so it's a function from the tangent space of delta to the n to the tangent space of Rn at each point. But here you can just think of it, it's just a linear map, because g was actually linear, so its derivative is basically equal to g. And so you can think of it as just a linear function, g lower star, going from this vector space W to the vector space R to the n. Okay. Now, this, if we just use the usual kind of Euclidean inner product on R to the 3n, we also get a corresponding inner product on W. And you can talk about the adjoint of this linear map using that inner product. So that's going to be the map G star from Rn to W. I guess you could also think of these things as matrices. So this is represented by some matrix with respect to the standard basis. This is going to be represented by the transpose of the matrix. Okay, so this is going back the other direction. Okay, so there's a bit of notation. So what we've got a volume maximization problem. We want to maximize the volume subject to constraints. The constraints are saying that we are inside the angle structure space. So the obvious thing to do again is to use Lagrange multipliers to solve this problem. So what have we got? We've got hyperbolic functions defined on delta to the n. That's a real valued function. The angle structure space is some nice submanifold of that. It's actually just yes, it's just a product of these triangles, but it's a nice kind of submanifold sitting inside Euclidean space. And what we want, at a maximum for volume, the restriction of this volume function should have a critical point. So we want the volume restricted to the angle structure space should have a critical point at a point x. Okay, so the question is, so how do you write this condition? Well, having a critical point on this subspace A, that's equivalent to saying that the gradient of this function v is perpendicular to A at x. Okay, so this is like the usual Lagrange multipliers argument. So what does that mean in our case? Well, that means that the gradient belongs to the orthogonal complement of the tangent space to A at this point. But now the tangent space, so what was A? A was just points where this function is equal to some constant. So it's a preimage of a point. The tangent space is just the kernel of the derivative of G at this point. So this is the same as the kernel of G star orthogonal complement. And in fact, if you remember, so from linear algebra, orthogonal complement to the kernel is the same as the image of the adjoint. So this is the same as the image of G star, just by some linear algebra. What that's another way of saying it says that we can write the gradient as this G upper star of lambda for some lambda in R to the n. And in fact, if you think of this so as some list of numbers, lambda 1, lambda 2 up to lambda n, these are just the usual Lagrange multipliers. Okay. So this is a fancy way of writing out the usual Lagrange multipliers argument. Okay. So that's what we get from using Lagrange multipliers. So any critical point of volume has to satisfy this condition. Okay. Now the next thing, we want to look at the edge conditions. So remember, to get a complete hyperbolic structure, we want the translations along the edges all to be 0. So the question is, how can we rewrite that in terms of angles? And there's actually a nice way to do this, just using the sine law from Euclidean geometry. So let's see. We want to think about what's a developing map look like around an edge. So you see, some Euclidean triangle, then the next triangle, so on. When you go around, the angle sum condition means all these angles add up to 2 pi, but we might end up with a different length to what we started with. So if we take, so the first edge here has got length L0, the next one's length L1, L2, so on. When we get back again, we get to some length Lm. And what we'd like is that L0 should be equal to Lm. But now it's just a little geometry exercise to figure out how to relate these lengths to the angles. So let's see. So if we take one of the triangles here around the centre, looks something like this. We've got some angle alpha I, beta I, gamma I. And this comes from the kind of a cross-section to a cusp in one of the ideal tetrahedra. Okay, the way I've labelled it here would have length Li minus 1 on the bottom, length Li on the top. Now we can just use the sine law. So we know, for instance, that if we look at this length divided by the sine of the opposite angle, that's the same as this length divided by the sine of the opposite angle. So using the usual sine law for Euclidean triangles, you get this equation. So Li over Li minus 1 is the ratio of sine of beta I over sine gamma I. Okay, so this is just Euclidean geometry. Now if we want to go from L0 to Lm, we just have to multiply a bunch of these things together. So it turns out the translation length along the edge is actually log of this ratio, Lm over L0. But in any case, so for no translation, Lm should be equal to L0, so log of this thing should be 0. So we want this t to be equal to 0 around the for each edge. Okay. So let's rewrite this. So log of this, you can write it as a sum. It's a sum of log Li minus log Li minus 1, where I varies over all the pieces coming together around the edge. Now, on the other hand, Li over Li plus 1 was the same as the ratio of sine beta I over sine gamma I. And I guess we get the same thing if we put in a factor of 2 there. So this is the same as the sum of log 2 sine beta I minus log 2 sine gamma I. Now at this stage, okay, to understand what this is telling us, we need to just remember, okay, what was the Lobachevsky function? What did that look like? Let me write it down again. So we had, so this was an integral. So things for integrating were exactly this function, log of 2 sine of t. So you can see the things I've got in this equation are exactly the things that come up inside a volume formula. So if you look at the derivative of this function, it's just going to be minus log 2 sine of theta at the angle theta. So you can rewrite this, and remembering the volume is the sum of all these Lobachevsky functions of the dihedral angles. So you can rewrite this. This is going to be minus the partial derivative dv by d beta I. The second term is going to be plus the partial derivative of d by d gamma I. Okay, I guess I didn't need to write this down. I've got it here. Okay, but so the derivative of this is minus log 2 sine theta. So we can rewrite this translation length in terms of derivatives of our volume function. So it's some kind of linear combination of entries in the gradient of the volume. And this is kind of one of the key observations. So we can, this no translation condition comes to some condition on the gradient, some sum of combinations of the gradient of the volume. Okay, so now we could rewrite this. So if you look at the form of this, you can see, you can rewrite it in, okay, so here's kind of a fancy way to say this. Translational holonomy around the edge. It actually looks like something like this. We had our original function g, which describes the gluings. That just tells you about the angle sums around the edges. And this thing that we were getting in the previous equation, it looks like something like this g star times a linear function j times the gradient vector, where j, it's some kind of linear transformation from w to w. The square of it, it's almost minus the identity. I guess the way I've normalised things here, you get minus 3 times the identity. And you can see kind of very explicitly from the previous formula, if you take j that looks like this. So the rows are things like 0, minus 1, 1, 1, 0, minus 1, minus 1, 1, 2. If you put in this matrix in the previous, you get things like these combinations. So alpha I corresponds to a term like this involving minus beta and minus plus gamma derivatives. So that corresponds somehow to this first row. Anyway, so we get this kind of nice description of the translational holonomies. It looks like this. Now at this stage, we have to use some sort of combinatorics of these ideal triangulations. And this goes back again to this famous paper of Neumann and Zagier from 1985. So in this, they work out some very nice sort of combinatorics conditions on ideal triangulations. And using that, we'll be able to see that the no translation conditions hold if we're at a critical point for volume. Okay. So if we combine the previous steps, okay, what do we get? Well, from step 2, we had the translational holonomies. It's given by some vector that looks like this. G star times j times grad v. That'll give you a vector with all the holonomies along the edges. Now from the first step, Lagrange multipliers, you can write this gradient as something like g upper star of lambda. So this is using the adjoint or transpose of this matrix applied to some lambda. And I guess now I'm just going to kind of quote this magic result from Neumann and Zagier. They tell us that this combination, so this g times j times g upper star, that's identically 0. So this is just coming from the sort of combinatorics of the triangulation. And once you know that, that tells you then that this whole thing's equal to 0. So all the translational holonomies vanish at this critical point.